Let's think about inverse functions. So let f be a function from a to b be a one-to-one function. In our previous video, we saw that a one-to-one function means that f of x has unique output values. No two different inputs can give you the same output. The inverse function is denoted this way, and this notation is admittedly poor because the exponentiation f to the minus 1 power is also sometimes used for division. So this is not equal to 1 over f, even though the notation might suggest that. You should be able to determine from context whether I mean division or the inverse function. But the inverse function is a function from b to a such that two things happen. Number one, if you compose the two functions, so if you put f inverse inside of the function f, if you compose them, you just get back x. And second, if you compose them in the other order, so if you put f of x inside of f inverse, you also just get back x. Let's see some examples. So the inverse to f of x, which is x cubed plus 1, is f inverse of x, which I'm saying is x minus 1 to the 1/3 power. It's easy to see why these two functions are inverses. You could just check condition 1 and condition 2. So condition 1 says, if I put f inverse inside of f, I should get back x. So doing that, I get x minus 1 to the 1/3 power cubed plus 1. If you simplify, you could see that the 3 and the 1/3 power cancel each other out. I get x minus 1 plus 1. The minus 1 and the plus 1 cancel each other out, and I just get back x. Similarly, if I compose them in the reverse order, I get x cubed plus 1 minus 1 to the 1/3 power. And again, that simplifies to x. When I think of an inverse function, I think of these two functions undoing each other. So if I compose them, they undo each other, and I get back what I started with. So if I plug in x, and I do these two operations, I end up with x. So I start what I ended with. Now, that's kind of what I was saying when I did this example. The 1/3 power and the 3 power undo each other, cancel each other out, and that minus 1 and the plus 1 undo each other. Let's see one more example. So the inverse to f of x is 1 over x is f of x is 1 over x. So what I'm saying here is this function is its own inverse. We could see this because putting one of these functions inside the other, or putting this function inside of itself, gives f of x is 1 over x, which is just x. So this function undoes itself. To undo division, you divide again. Let's write down a step-by-step guide on how to find these inverse functions. So here is how to find f inverse for a one-to-one function f. So it's a 3-step process. The first step is I'm going to let y equals f of x. Step 2 is I'm going to solve for x. And step 3 is I'm going to say that now what you're going to find is x is equal to the inverse function evaluated at y. So let's see an example of how to follow this step-by-step procedure. Let's say I let f of x equal 2x plus 4. Then what happens? I'm going to do y equals 2x plus 4. So that's my step 1. I'm just going to let y equal this function. Step 2. I'm going to solve for x. So to solve this for x, I think you need to subtract 4 on both sides and then divide by 2. So if I subtract 4 on both sides and divide by 2, I believe I will get 1/2 y minus 2 is equal to x. Step 3 says I've identified my inverse function. Now I have x is equal to some expression involving y. That expression is the inverse function evaluated at y. So we have f inverse of x is this expression where every y and x are replaced. So I get 1/2 x minus 2. There's the inverse. Now if I were unsure if I indeed had the correct inverse, I could go back and check condition 1 and condition 2 and see that these two functions indeed are inverses. Let's try this one more time. So let's say I let f of x equal 2 over 3 minus x. So I'm going to follow my 3-step process. The first step is letting y equal 2 over 3 minus x. Then I can solve for x. So solving for x, I'm going to multiply both sides by 3 minus x. I'm going to divide both sides by y. And if I simplify a little bit, I think you'll find that x is equal to 3 minus 2 over y. And so therefore, my inverse function is 3 minus 2 over x. Now the graph of f inverse is the graph of f of x reflected about the line y equals x. So if you know the graph of f, then you can use that to draw the graph of f inverse. Let's see what this means graphically. So I'm going to say that I have a function on the interval from a to b, and let me sketch the line y equals x. That's a diagonal line going like this. So there's the line y equals x. So I'm going to draw the graph of a 1-to-1 function. Actually, let me move b to over here so I don't have to redraw my picture. So on the interval from a to b, I have a 1-to-1 function f shown here. The inverse function has graph that's reflected about the line y equals x. So I'm going to take this picture and kind of fold it over, and I believe I will get a picture that looks like this. That's supposed to be the same graph just reflected about the line y equals x. Why is that? Well, if you think about this process to find the 1-to-1 function, what we're doing is reversing the roles of x and y. So we're flip-flopping the x and the y. That's why this condition about the graph is true. Now, if you look back in the very beginning, the first sentence I wrote down in this video was that f was a 1-to-1 function. So let f be a function from a to b that's 1-to-1. And further down here I said how to find f inverse for a 1-to-1 function. The reason why I said that is because the inverse function can only be found if you have a 1-to-1 function. If you don't have a one-to-one function, it's not possible to find an inverse. If you think about this graph down here, you could see why. Every function must pass the vertical line test. So to be a function, the vertical line test must be passed. The graph must intersect each vertical line in at most one place. If your function is one-to-one, it also additionally satisfies the horizontal line test, meaning the graph intersects each horizontal line in at most one location. So if you take this graph of the function and you flip it about the line y equals x, horizontal lines become vertical lines and vertical lines become horizontal lines. Therefore, in order for this red inverse function to pass the vertical line test, the original pencil function must pass the horizontal line test. Okay, so there's a very brief introduction to inverse functions.